recorded videos with you all. Sorry for that. Okay. Here, when it comes to network problems, majorly, I would call it as here, let me put it here. Network flow problems, right? In network flow problems, when it comes to nodes, okay, nodes can be supply points, or nodes can be demand points, or nodes can be transshipment points. Okay, these are the three nodes which exist. Okay, and if you want to transport anything, any unit, say you're manufacturing ship or sand or whatever, right? Any unit that is manufactured flows from node I to node J. And when it flows from node I to J, there is a cost associated. That cost, you call it as cost of Ij. Between node I to node J, when a unit flows, okay, it's called as cost. And cost can be monetary payment, it can be distance, or it can be some other measure, whatever be that measure. And majorly, the objective function or objective here would be to minimize the cost or minimize the distance, or whatever be the measure that we're using, we need to minimize that. Again, these kind of problems are called as minimum cost network flow problems. Network flow problems or minimum cost network flow problems. And whenever we work on these problems, it is always advisable to balance the flow. Meaning, if you have total supply, if it is greater than total demand, then you'll have a rule at each node. This rule at each node would be inflow minus outflow should be greater than or equal to supply or demand. First thing that you need to remember. Second, if total supply is equal to total demand, then the rule at that node would be inflow minus outflow is equal to this. And if total supply is less than total demand, then the rule at that node would be inflow minus outflow would be less than or equal to supply or demand. Okay, so this first thing also, let's put it this way. this, then let me put equal to, then let me put this. Okay, next. Let's look at transportation problems first. Let me now get back to the transportation problem. Okay, in this we'll look at both transportation, then we'll look at assignment, then transshipment, then shortest path, then okay, let's go on. Here, I think already we have discussed about the specific use case. Let me see if I can open any spreadsheet which we have used to save. Yeah, this is what we have discussed. Okay. So say we have wine which is getting manufactured, and we have wineries in, say, Cape Town, Johannesburg, and George. 75 whatever tons, or however you know whatever term you use for measuring this particular wine can be used. 125, 100. So in total you have 300. Then you have distribution centers also. They supply to 4 cities, city A, B, C, D. How many liters of wine is supplied is provided here. Here, total supply is equal to total demand, right? So supply equal to demand. This is what we are looking at. Total supply equal to total demand. That means inflow minus outflow equal to supply or demand. And you have the current shipping plan. This is the current shipping plan. Okay. You have all the 4 cities and you have the winery. Here, these are the 4 cities that you have, and these are the shipping costs. Let me put it here. So you have the shipping cost as well. We have winery and we have cities. Okay, and you have the supply and demand. These are the costs that you have. And then you have supply and demand. And these transportation problems have certain assumptions. What are those assumptions? Each source has a fixed supply of units. Each source has a fixed supply of units. That means entire supply must be distributed to the destinations. So for example, if your supply here is 75, Cape Town, entire 75 has to be distributed to all these cities. If you have 125, entire 125 should be distributed. If you have 100, entire 100 should be distributed. That is one assumption. Next assumption is each destination has a fixed demand for units. So that means entire demand must be received from the sources. If this is the demand for the city, entire demand must be supplied from these sources. Entire 65 must be supplied from these sources. Entire 70 must be supplied from these sources. Entire 85 must be supplied from these sources. And when it comes to transportation problems, there is something called as feasible solutions property. What feasible solutions property means is you'll have a feasible solution if and only if the sum of supplies equals the sum of demands. Okay. If sum of supplies is equal to sum of demands, only then you'll get a feasible solution. And also we have certain cost assumptions. What are those cost assumptions? The cost of distributing the units from any particular source to any destination is directly proportional to the number of units distributed. So cost of distributing units from any source to any destination is directly proportional to the number of units distributed. It doesn't work this way that, hey, if you distribute more units, then the cost will be less. Right? Usually, if you transport more in one vehicle, the transportation cost will be the less. If you transport one say table or 10 tables, cost of truck, cost of transportation will remain the same. But such assumption, such a condition doesn't exist there. So cost is equal to unit cost of distribution, means each liter of wine that you transport multiplied by number of units distributed, number of liters that you transport. So this is one assumption that we need to bear in mind. So any transportation problem, right, must satisfy these things. These assumptions, feasibility solution, cost assumptions. Only then you can proceed further. Here, in our business problem, okay, what are the decision variables? That's the point that we need to worry about. Decision variables are the amount of gallons or the number of liters that you want to transport from one location to another. Okay, you guys have to do this, by the way. By tomorrow, you have to submit it. Okay, decision variables. Please look at this. Okay, here, let me write it down. Xij is a decision variable, which is nothing but amount of wine shipped from I to J, where I is the binary, J is the distribution center. How many I do you have? 1, 2, 3. How many J do you have? 4 cities. 1, 2, 3, 4. And you have an objective function. Objective function here is to minimize the cost. Okay, if you want me to put down the decision variables, right? I can probably put it this way, wherein I would say I have 3 binaries. Okay, what are those 3? These 3. Okay, we have 3 binaries. I will call this binary as I, okay, for our understanding. When I say I equal to 1, it is first line. When I say I equal to 2, I equal to 3, you have 3 binaries. Done. Then you also have distribution centers. We have 4 distribution centers. So let me know them. Distribution centers. I'm going to call distribution centers as J. Okay, let me take it up. This will be it. Okay, here. When we say J equal to 1, and you'll have J equal to 2, 3, 4. What are these J? J are nothing but distribution centers like city A, city B, city C, and city D. Let me do all of these. Okay, done. So these are your decision variables. Okay. Then we have an okay, you also need to record constraints, but let's write the objective function. Objective function is to minimize the cost of transportation. Transportation cost. This is transportation problem that we are trying to solve. Okay, here you need to record what the cost of transporting from Cape Town to city is 464. So it'll be 464 multiplied by how many ever gallons you want to transport plus 513 multiplied by how many gallons you want to transport or how many liters you want to transport from Cape Town to CTB plus this is the cost and how many ever liters you transport plus this is the cost for the number of gallons you transport, right? In that way, I'll become a lengthy thing if I multiply this 352 multiplied by this plus this multiplied by this and all that. So an easy way out is I'll say a sum product in Excel. I want to multiply all of these, comma, with what? With all of these prices. Job done. Why did you get 0? Because initially we're not putting anything here. We're just letting it remain blank. So this happens to be our objective function. So we need to record, friends. You always add a comment so that it's known to people on what it is. This is the total cost to be minimized. Okay, this is what objective function. Done. Okay, when you hover, you know what that means. Then constraints. We should not forget the constraints. Okay. We also have constraints. What are the constraints now? We have supply related constraints and we have demand related constraints. That means whatever J you're transporting from one location to another, summation of all these things should be equivalent to the total supply. What is the total supply? Total supply is 300 gallons. That's a supply related constraint. And demand related constraint is, okay, let me put it here. Supply constraint is that I'm just wondering on how do I show this to you guys. One second. Okay, let me write it down. Then we'll put it in Excel days. Okay. So if you take I equal to 1, then x11 plus x12 plus x13 plus x14 should be equal to the supply at that unit. So what is it that you're supplying? 75. It cannot be more than that, right? It should be exactly equivalent to that. And then when I say I equal to 2, which is the second, then x21. 21 means 2 to city 1 plus x22 means from 2 to 2. x23, x24 should be equivalent to 125. Then when I equal to 3, 31, 32, 33, 34, right? Summation should be equivalent to 100. Yeah, that is what it is. So let's write down. So it's nothing but all these things, summations of all these things. So that when you take a summation of all these things, it should be equivalent to 75. Okay. Total supply. Total supply supplied and total supply possible. Then here also you put another constraint. Same thing. Summation of all these values. 125. Right? That's should not be more than that. Then again, you give summation of all these. How many ever liters of wine you want to transport? It should be equivalent to 100. Okay. Then we also have demand related constraints. What are demand related constraints? Let me write it down. For every distribution center, let's say J equal to 1. For J equal to 1, x11 plus x21 plus x31. From here to here, from here to here, and here to here should be equivalent to exactly 80. It cannot be more than that. Demand for that center city is 80 only. Then x1, 2 plus x22 plus x32. For city B, whatever you can send would be only 65. Then if you take J equal to 3, x13 plus x23 plus x33 would be equivalent to 70. Then if you take J equal to 4, x14 plus x24 plus x34 will be equivalent to 85. That's it. These are called as demand constraints. Total demand and total demand met. Okay. So you again do the same thing. Summation of all these three to city A would be equivalent to 80. It should not be more than that. Then if you say summation of all these three should be 65, not more than that. Should be exactly the same. Then summation of all these three should be 70. Then summation of all these three should be 85. Okay. And of course, there will be non-negative constraints. Non-negative constraints are different constraints. I mean, it cannot be negative, right? Whatever you are going to supply cannot be negative. Values can be 0 or you might not have. Okay. So, here, one more thing is we need to bear in mind the integer problem. But okay, let's not put that. Now, what we can do is, given all these things, you just go to data. Okay, you click on solver. What do you want to minimize this? Right, that's your objective function. We want to minimize by changing what? By changing how much quantity you can transport to each of the cities. But then we need to put constraints also. What are the constraints? This value should be equal to 75. Okay, next. This value should be equivalent to 125. We added the constants. Let's add more. So this value should be equivalent to 100. Click on add. This demand value should be equivalent to total demand. Again, add another thing. This is equivalent to 65. Add. This value should be equivalent to this. This value should be equivalent to this. Done. Non-negative constraints, simplex problem solved. There we go. What's happening? From Cape Town, from Cape Town, in Cape Town winery, you can produce 75 liters of wine, assume. So you transport it to city B and city D. Total will be 75. So entire 75 is used. Tick. Then you're going to Johannesburg. You're saying, okay, 125 is there. Transport to city A and B. So entire 125 is used. Wonderful. Then you go to George. You have 100. So you transport it to city C and D. 100. Job done. Everything is utilized? Yes, everything is utilized. So entire 300 is utilized. Wonderful. Now let's see whether each city got the entire thing or not. City A should get 80. Did we get 80? Oh yeah, we got 80. Tick. City B should get 65. Did we get 65? Yes, 65. City C should get 70. Did we get 70? Yes. Tick mark. City D should get 85 liters. Did we get 85? Yes, 85. So entire 300 is achieved. Done. And this is the minimum cost that you can incur given the cost of transportation. Given the cost of transportation in dollars, $464 is what it will cost for 1 liter of wine from Cape Town to city. So given that context, this is the minimum cost that you're going to incur, and this is the transportation route that we have given. Right? Clear, friends, or do you have any doubts? Abhijit, Akhil, Ankita, Chinna, Fahad. Very important. Please ask. Yeah.
Clear, clear.
Okay. Because you'll be working on a project, and let me tell you now that, yeah, whatever be the network, similar thing that you have to do, there is a business problem, friends. Okay. Which I have received from one of the customers. We need to solve it. Simple. We need to solve this business problem. And already one of our participants is working with the client. If you people can solve it,